So there's one explanation which I owe you from the previous hour, and there are several ways to write it down. You can find one way in just in the beginning of chapter 12 of my book with Levin and Wilmer, but here is another way to say it. You start with the measure concentrated at x, and we want to look at its density with respect to pi and compute the L2 norm in L2 of pi. So there are lots of pi's around. And then when you do that, you only get the contribution from x. You have to take 1 over pi x squared and multiply by pi of x, so you get 1 over pi x. So that's the L2 norm of the density when you start at x. Now, if we subtract 1, which is the density of pi itself, then we're going to get a contribution which is smaller. We'll just get a -1 here. So the reason for that is if we take delta x over pi and expand it in terms of the right eigenfunctions, then the first summand here is just f1 is 1, and the coefficient of 1 is also going to be 1. So from that you see that this norm squared is just going to be 1 less than 1 over pi x. Now when you apply p to the t and compute the norm squared of that, the effect is going to be to I'm taking these fj's to be normalized in L2 now. So the effect will be to take the if I took t equals 0, the norm squared would just be the sum of aj squared for j from 2 and on. But when I apply p to the t, the effect on the norm squared is to multiply by lambda j to the 2t, because fj is a eigenfunction, and p to the t fj is lambda j to the t times fj. So you get this sum, from which you can pull out a lambda 2 to the 2t. So I'm okay, and maybe let's put absolute values. So okay, so let's consider the case when the lambda j are between 0 and 1. Otherwise, the main eigenfunction might not be lambda 2, so you need the notation. So consider the lazy case, or the case where the eigenfunctions are positive, eigenvalues are positive. Otherwise, the main eigenfunction may not be lambda 2. It may be. This argument still works in the general case, but then instead of lambda 2, I just have to write the largest eigenvalue in absolute value. So what you see here is you get lambda 2, or more generally the largest eigenvalue in absolute value, to the power 2t is multiplying this 1 over pi x. Now, what is the mixing time? It's the time when the total variation norm is less than epsilon for any starting point. Now the total variation norm is half the L1 norm, and the L1 norm is when you work in a normalized in a probability space. If I have a function f and I compute its norm in L1 of pi, that's less than the norm of f in L2 of pi, when I take pi to be the normalized stationary measure, which is what I'm doing now. So that's just the Cauchy-Schwarz. So in order to get the mixing time to be less than epsilon, I want the norm of some function to be less than epsilon. It's enough to take the L2 norm to be less than epsilon. And so you basically want this to be less than epsilon or less than 2 epsilon. And if you think, when does such a, so the kind of inequality we want this to be less than 2 epsilon. So forget the -1, that's really negligible here. So really you want lambda to the 2t times 1 over pi x to be less than epsilon. So if you think what time do I need for that, and just take logarithms, you'll get that the time you need is the relaxation time, the difference of lambda to 1, multiplied by log of 1 over epsilon pi mean, which is the formula we had. So then all this is treated slowly in the book, so I'm not going to go over it, but it's just taking this inequality, taking logarithms, and use the fact that log of 1 minus delta is close to minus delta, and you're done. Yes. That's right, the holding state of 1/2. This is just the device to get rid of periodicity issues. Yes. You could do other holding times, but that's a convenient choice. Okay, so now, has anyone done the exercise? Why the d log d? Okay, well.
So you are looking for the coordinates, and first time you get a coupling on a coordinate, you actually collect that coordinate, and then you because of the Markovian property, you can start afresh looking for the next coordinate.
Right, but if I really look, I want to first match the first coordinate, then the second and the third in order. That will really take the d squared.
Yeah, no,
so we want in a kind of
whichever first coordinate I can choose.
Right.
Then the next different.
Right.
So first, so I can look at the first time when one of the coordinates couple, and starting from then on I look at the next coordinate that couple.
Right.
It need not be the original 1 to n.
Right. Yeah. So
that's where the coupon collector comes.
So that is related to coupon collector. That's right. However, that's right. So
you use Markovian property to sort of split things.
So the thing is, I don't have the time. Right. So each time there's some scaling here, right? Because in one step I'm not guaranteed to. So in the coupon collector, in each step you get a coupon. Here we have this different scaling, but one can do it this way. Right. Now, that's right. That works. Another way to explain it is if I just focus on one coordinate and ask say tau 1 is the coupling time for, say, the first coordinate. So this is not the first to couple, just the first in the original ordering. Suppose I look at this. What is... Now, we already argued that the expectation of tau 1 is at most d times n squared over 4. Right? So this we've argued, and this is true for, 1 is just an example here. This is true for any one of them. So so similarly, we could define tau I is for ith coordinate, and then tau is just our coupling time is just the maximum of these tau I. Now, the probability that tau I is bigger than dn squared over 2, this is twice the expectation, so this is at most a half. And now the same idea of experiments, if it tells us that the probability, if I put here k times this, then I get half to the k. Right, so I just weight time dn squared over 2 with probability half. I couple the first coordinate. If I don't, I weight another dn squared over 2, and it's again true. So so suppose I'm just going to make this to be small enough. How small? I want this to be small so I can add this up over all coordinates. So if this is say less than 1 over 4d, then we're going to be in business. So this tells us right, so we want 2 to the k to be bigger than 4d. So k should be at least 2 plus log base 2 of d. And if we make k this large, then we will have this inequality holding. But now, the probability that tau is bigger than this number k dn squared over 2 is going to be, now we can just apply a union bound, right? This probability is just bounded by the sum I from 1 to d of the probability that tau I is bigger than the same quantity. Right? And this we've already bounded by, so this will give you d over 4d. So this will give you a quarter, which was our arbitrary criteria. And of course, you could do this with any epsilon that you want. Okay? And this approach will actually give you, if you want the right dependence on epsilon. So if you care about getting epsilon, you'll get a log 1 over epsilon. So it's actually very close to coupon collector, because one of the ways to do coupon collector is, one coordinate at a time. The other one is just, looking at each coordinate and using tail bounds. Okay? So those who want still to have something left from the exercise, show that this is really the right order. So the mixing time is indeed of order d log d times n squared, so get a lower bound. So it's fairly easy to get the lower bound of dn squared just by, again, looking at one coordinate. But to get the log, you need some kind of cooperation of all coordinates. So this is more tricky. Okay, I would say that's a pretty hard exercise to do from scratch. There is a method. So there are various methods for lower bounds. There is one called the Wilson's method for lower bounds, and which is in one of the chapters in my book. And from that, it's easy to derive this. But just to prove it directly without any tools is quite a challenging exercise. Okay. Now let's go to actually a simpler problem of the same type, but we're changing the perspective. Instead of thinking of n as growing and d as a large constant, we're going to think of n as fixed and d as going to infinity. So this is going to be random walk on the hypercube. Simple and useful example. So here we have lazy walk on the hypercube. We have n coordinates. They are bits. Each time we choose a bit and refresh it. So because we're doing a lazy walk, refreshing the bit doesn't mean flipping it, means replacing it by a random bit. So a fresh random choice. Okay, so this is the lazy walk on the hypercube. So it's kind of a special case of what we just discussed. So the natural coupling we have two chains, or two particles. Each one corresponds to a vector in the hypercube. We choose which coordinate to update. We're going to update the same coordinate in both. And the update will be to choose the same. How do we update a coordinate? We toss a coin and put that value of that coin in that coordinate. We're going to just update them with the same coin toss. Okay, so we use the same bit in both the x and the y particles. So this is now leading directly to coupon collector. We have the time when the two chains couple is exactly the time when we have touched all coordinates, because each time we have chosen a coordinate, the bit there agrees. So it's a simpler problem than the previous one we discussed. In fact, it's a special case, and it maps directly onto coupon collector. Okay, so that's why in the d-dimensional hypercube, or here I switched, I call the dimension n. Anyway, in the d-dimensional hypercube, we get the upper bound of d log d. So, and okay, this is again the dimension. Since we now don't have only one parameter, the dimension, it's now been called n. And this is the same argument we've seen. So if ak of t is the event that the kth coupon has not been collected, we get this e to the minus t over n, and we get a bound for the coupling time, which tells us that indeed the mixing time is at most n log n. Because the hypercube is such a simple example, we could be more ambitious and ask, what is the right constant in the mixing time? So we know the right constant in the coupon collector is 1. That is, to collect all coupons, you need n log n. The question is, to mix in the lazy hypercube, do we need n log n, or maybe a smaller time would suffice? It turns out in this example that the order n log n is right, but the constant is not sharp. The sharp constant is 1/2. So the mixing time in the lazy hypercube is asymptotic to 1/2 n log n. And this is an example of the cutoff phenomenon that I'll describe more towards the end of the course. Because usually when we talk about mixing time in examples like the cycle, well, the choice of epsilon equals a quarter is arbitrary, and t mix of epsilon really depends on epsilon. If you make the epsilon smaller, the mixing time will get larger by some constant factor. That's not the situation in the hypercube. In the hypercube, it turns out that t mix of epsilon is always n log n over 2 plus a lower order correction. Let me write down the formula. So in the hypercube, in the lazy walk on the hypercube, what turns out is the mixing time, t mix of epsilon, is very close to n log n over 2. So if I take this and subtract n log n over 2, this difference is less than some constant times n times the log 1 over epsilon. So the correction, there is some t mix of epsilon has to depend on epsilon, but that dependence is of lower order. It's only linear in n. So the mixing time is really n log n over 2 gives you the right order. And you might wonder, where is the half coming from? Because the coupon collector is really, if you want to collect n coupons, it's really, you need n log n. Yes?
Is it because to start with some of the coordinates is same for both the walks?
That's not it. No. So it's true that some of the coordinates are the same, but still about typically, there are two things. One is, we're talking about worst case coupling. So we have to take x and y, which are also all zeros and all ones. And second, if I'm concerned with typical x and y, I will get, right, they differ in n over 2 coordinates. But this is not the reason for the half, because suppose I have two vectors that differ in n over 2 coordinates. Each time I'm picking a coordinate at random, including one of those where they already agree. So even the time until the if I have a coupon collector and he only has to collect, the first n over 2 coupons, but each time he gets one of the n coupons, the time to collect just the first n over 2 will not be n over 2 log n, it will still be order n, not just order, the constant will still be 1. So it's not because some of the coordinates agree. It's because he doesn't really need to collect all the coupons. And so, but that requires a different argument. So to apply this coupling argument with this very simple coupling, you need really n log n. So this coupling time really is n log n without the half. To get to the half n log n, you need a different argument. You cannot just use this, this simple coupling. So there are two ways, or there are multiple ways to get it. One is to use the spectral representation. We know on the hypercube all the eigenvalues, all the eigenvectors, and we can just use that to write the transition probability explicitly and calculate. That's one method. It's fine, but it doesn't really give you much insight, and doesn't generalize well to cases where you can't compute so precisely. But let me explain, at least intuitively, the idea why half n log n is the truth here. I have n coordinates, and I really want to think of randomizing them all when I choose n. So if I pick them all, they all get randomized. Suppose I wait for time n log n over 2. How many coupons will the collector miss? He will, in n log n over 2, half the time, he will collect all but root n of the coupons. Okay, so that's a classical calculation. And now if I wait a little longer, so n log n over 2, plus, say, instead of n log n over 2, suppose I wait n log n times 0.51. Okay, then the number of coupons he didn't collect is going to be n to the 0.49. Now, if I take a vector of IID bits and I choose a set less than root n of them and make those 0, and the locations of where I choose are uniform and random, I cannot tell this apart from a uniform vector. So this is connected to the fact if I have a binomial distribution and I shift it by less than root n, then the total variation difference between the binomial and the shifted one is going to be little o of 1. So that's the intuition, and we'll make this more precise later. Okay, so a alternative to coupling is called strong stationary times. Till when do we have? 11:20. Okay. So another method besides coupling that is very useful and intuitive is the method of stationary times and strong stationary times. Now, in the hypercube, this is very close to the coupling we just discussed, but it is not just about the hypercube. So one notion that will be important here is stopping times. So, of course, you're familiar with if I have a sequence of random variables, a stopping time for the sequence is some variable where the event that tau equals k is determined at time k, is a function of x1 to xk. Here we'll want to consider what's called randomized stopping times. The fancy language is these are stopping times in a larger filtration, but another way to think about them is that these are stopping times for a process I use to generate the chain. So we can use the example of this hypercube. So let's look at the random walk on the hypercube, the lazy walk on the hypercube as I described it to you. So we choose a coordinate and we refresh it. Then we choose another coordinate and refresh it. And I want to use the stopping time, which is the time where I chose all the coordinates. So the delicate point about the stopping time, it's not a stopping time for the original process. Because if I chose a coordinate and I decided not to change it, right, so the coin fell that I'm not doing, then I cannot tell just looking at my process on the hypercube which coordinate I chose, because nothing happened. So it means that, but in order for in this definition of the stopping time, I said I stop when I've selected all coordinates. I cannot tell if this has happened just looking at the process on the hypercube itself. So you need to use what's either called a larger filtration, or in our case, just a different sequence of random variables, which is used to generate the Markov chain. So these are two perspectives that are equivalent. Let me describe this one. So when we actually want to run a Markov chain, say on your simulate it on a computer, how is that done? You have you know some transition matrix, but in order to choose what transition to actually make, you generate a uniform variable. Say your computer gives you some pseudo-random numbers, which you regard as uniform variables. And if you have to make an experiment where you have, you have the transitions, you are at a certain x, and you have to transition to y according to pxy, you'll just partition the unit interval and make the choice according to where your uniform variable landed. So this is known as the random mapping representation of a Markov chain. If I am now at xt minus 1, I want to move to xt. I can always do that by making some independent random pick and then have a deterministic function of my current state and this independent random variable. You can always realize any Markov chain using this rule. For instance, for the case of the hypercube, our z will consist of which coordinate to refresh and so z is which coordinate to select, and then the bit we are using to refresh it. So z will have, given our current location, what we need to know to refresh is what coordinate we are now refreshing and what bit we want to put in that coordinate. And then we have a deterministic function that moves from the current state choices to the next state. Okay? And then our stopping time is a stopping time for this sequence. Okay. So finally, what is a strong stationary time? It's a randomized stopping time with this property. So what does this property mean? So the probability tau equals t and x tau equals y should be the probability tau equals t times pi of y. It's more understandable if we just divide by probability of tau equals t on both sides. And what we see, what this means is the probability that x tau equals y, conditional that we stopped at time t, is just the stationary distribution. What?
For your Markov chain.
Right. For my Markov chain, z only takes finitely many values, but you can have z be continuous, that's fine. I mean, in a finite Markov chain, you can always make z only takes finitely many values. But okay. So strong stationary times have the property that when I stop, I am at the stationary distribution, and it's true even when I condition on the stopping time. Now, more generally, one can define a stationary time as a time where if I look at the chain at that random time, the chain has a stationary distribution. These are also useful, but harder to work with. Here is an example of a stationary time that's not a strong stationary time. Take any Markov chain, pick a state according to the stationary distribution, according to pi, and run until you hit that state. Okay? So this is going to be, by definition, a stationary time. When you hit that state, you're at a stationary state because that's how it was chosen. Okay? But it's not a strong stationary time because if you know that you stopped at time 0, you know, well, the choice was the starting point. Or if you know you stopped at time 1, you know you're at one of the neighbors of the starting point. So that information of when you stopped biases the distribution. A strong stationary time is immune to that. So it's a more powerful concept, but also more restricted. So our example from the hypercube is a strong stationary time. We wait till we touch all coordinates. It doesn't matter. So we know that minimum time is n. The expected time is n log n to touch all coordinates. But it doesn't matter if I tell you this happened very quickly in n steps or it took a long time. whenever it happens that we touch a coordinate, at that time, even if I know what that time is, I'm still completely uniform over the hypercube. It's very easy to check that. So that's a strong stationary time, but as I said, not all stationary times are strong stationary. And for strong stationary times, we have an upper bound that the total variation distance at time t is always bounded above by the tail of the strong stationary time. So just like with coupling, but I want to emphasize, this is a common mistake, this kind of inequality is not true for stationary times. So to see a simple example, suppose I have a bipartite graph. So, and I do a chain which is not lazy. So that chain, in fact, never mixes. The mixing time is infinite. And there is no strong stationary time, because at any time, if you give me the time, I know I'm in the even sides or the odd sides. But the waiting until you hit picking a point according to the stationary distribution and waiting till you hit it, that is still a stationary time. So you cannot, so bounding the mixing time can be done using strong stationary times, but not using stationary times unless you have additional conditions.
Sorry, very naive question.
Yes.
Do there exist examples of Markov chains where there is no strong stationary?
No. There always is a strong stationary time. So and in the reversible case, there always is a strong stationary time where its expectation is of the same order as the mixing time. That's not true in the non-reversible case. So when I say always, I mean for aperiodic irreducible chains. Let me give you an example of a strong stationary time for any chain. This is not going to be as it's very useful for quantitative bounds, but just conceptually. So if I have any irreducible aperiodic Markov chain, if P, this is not a good one. If P is irreducible aperiodic, then there is some K so that P to the K is positive everywhere. So I can write P to the K as some epsilon times the matrix of all ones. Let me put the all 1 over n plus 1 minus epsilon times some matrix Q. Right, so any irreducible aperiodic chain, it means that there is some power of the matrix which is positive everywhere. And so call its minimal element epsilon over n. Okay, so I can write P to the K as epsilon times this plus 1 minus epsilon times some other non-negative matrix. Okay. Now this other non-negative matrix Q is defined by this formula, but it's also going to be a stochastic matrix. Okay, so there exists an epsilon where there exists a K where this holds with some positive epsilon and some non-negative matrix Q, which because of this formula, it will also be stochastic. So if you want to add a row, because this is stochastic and this is stochastic, right? So this is the matrix of all 1 over n's. Everything is 1 over n in this matrix. So Q is also a stochastic matrix. So taking a step in P to the K is like taking K steps in P. But that can be implemented as follows with probability. So this I wrote. Okay, the 1 over n I want to do. Okay, in general, this is for the uniform case. Actually, what I want is going to be a little different. I'm sorry, epsilon times. I'm going to put. So this is in the uniform case. In general, what I want is to write it this way. So I'm sorry, I don't want this representation. I want to write it in this way. So I have this is the matrix where all the rows are copies of the stationary distribution pi. And so this is again a stochastic matrix. So the same, so again, p to the k is all positive. So there is some epsilon where such a representation holds with q a non-negative matrix, and then q itself is stochastic. Sorry, that's the representation I want. And now, here is a strong stationary time. So to build it, we have to think of moving p to the k is equivalent to the following experiment. Toss a coin. This is a biased coin. Probability epsilon, it falls heads. 1 minus epsilon tails. If it falls heads, you just move to the stationary distribution. You select a state from the stationary distribution. If it falls tails, then you apply Q. You make a pick according to Q. So this is completely equivalent to just moving k steps in the original chain P because of this representation. But now I can define my strong stationary time. I wait till the first time this biased coin fell heads. At that time, by definition, I'm moving to a choice from the stationary distribution. And no matter, even if I tell you what this time is, still, it's chosen from the stationary distribution. So this is a kind of concept, soft proof. It doesn't give you anything quantitative useful, because if I knew what is this k, I already understand everything about the chain. So it's not useful, but it just tells you that this object always exists. What you want is to find a good one, and this is not the way to get a good one. Okay, but since you asked, I decided I'll tell you. Okay, so here is another celebrated example of a strong stationary time, and this is in top to random shuffle. So this is a non-reversible chain on the symmetric group. So we have n cards, and our configuration is just the ordering of the cards. So we have n factorial states. And how does the chain move? So this is called top to random. We take the top card and remove it and insert it in a random position in the deck. So after we remove it, we have n minus 1 cards with n positions, because we can put it in the very bottom or in the very top. So there are n possible positions to insert. The former top card is inserted in one of these n positions, equally likely. Okay, is this chain clear? It's called top to random insertion. And we want to, this is not a reversible chain, but we can still look for its mixing time. And it turns out the mixing time is again order n log n. In fact, it is, in this case, it's n log n with the constant. The constant is 1. To see the upper bound, we use a strong stationary time, which is the time when it's written there, the original bottom card has moved to the top of the deck, plus 1. So what you can easily check by induction, each time the original bottom card moves up, the cards under it are in random order. So their relative order, if you fix what is the set of cards under this, but look what is the relative order, it's uniform. Because when each one comes in, it could come in at any location. And if you continue this by induction until this original bottom card reaches the top, then all the other cards are under it, and they're in a random ordering. Now you're taking this card, which is the original bottom card, so it's a very special one, and moving it out and putting it in a random location. So now you'll get a completely uniform choice, and so you have a strong stationary time. But the expectation of this time is closely related to even the distribution, because how long the original bottom card, how long does it take it to move one step up? Well, let's say something has to fit under it, and this has probability 1 over n in every step. So you have to make it geometric with parameter 1 over n until the bottom card moves one step up. Once it moves a step up, there's 2 available locations under it, so now it's a geometric with parameter 2 over n, and so on. So you just have the time from the bottom card to rise is the sum of these geometrics, 1 over n, 2 over n, 3 over n, the same sum that you see in the coupon collector problem, and the expectation leads to the n log n. Now, one question which is surprising that it can be answered is what is, in many cases, what is the optimal strong stationary time? So I think I have, let me see if I have something about this in the slides. Okay, so suppose that tau is a strong stationary time. So this means x, so this can be written as follows. X tau has distribution pi, and tau independent of x tau. Because given, that's equivalent to what I said before, because it means even conditional on tau, x tau still has the same conditional distribution. So this is the same thing. Now, suppose I want to bound from below the probability that xt equals y. So this is bigger than the probability that tau is less than t and xt equals y. But if tau is less than t, then at time tau we're at the stationary distribution, and after we're at the stationary distribution, we stay at the stationary distribution. So this is going to be equal to pi of y times a probability of tau less equal t. Okay, so this uses the definition of strong stationarity, in that form. Okay, so if I now look at the difference, pi y. Okay, so let's divide by this difference is, so from this it's at most, well, it's at most 1 minus this probability, which is just the probability of tau bigger than t. Okay, so a strong stationary time always satisfies this quantity. This is known as the separation distance of the chain. This is at most the probability of, starting from x, of tau the tail probability of the strong stationary time. So, okay, now a strong stationary time, I'll abbreviate like this, is optimal if this is an equality for all choices of x, y. So if this inequality is equality, for all choices of x, y. Now, of course, if a strong stationary time is optimal in this sense, so its tail probabilities are as are okay. So yeah. So the separation is to minimize right. The tail probabilities are always bigger than this Sxt. If I have this equality, then it means the tail probabilities are as small as possible. And in particular, the expectation is going to be small as possible because the expectation of a positive variable is just the sum of the tails. So here is one fact. So y is called a halting state for tau and x if the hitting time say ty satisfies tau less equal ty almost surely px. So a halting state depends on the starting position and strong stationary time, or station in general. We could define it also for any stopping time. So a halting state is a state where if we hit it, then we know we have stopped. So tau must be less than ty with probability 1 when we started according at the state x.
So tau is any stopping time?
Tau is any stopping time, yeah. We will want to apply it with stationary times, but this definition is for any stopping time. Now let's see some examples. We look at the hypercube example. Suppose they start at all 0 vector. And remember, what was our tau? Our tau was the first time when all the coordinates are touched. Can you tell me some halting state for that? For the starting position, all zeros, and the stopping time when I've touched all coordinates. Is there a halting state? All ones, right? If I reach all ones, I surely have touched all coordinates, right? Of course, I can touch all coordinates much before, but that's a definite sign. Okay, so that has a halting state. Now here's the beautiful fact: when if there is a halting state for a strong stationary time x, tau, and all x. So when I say for each x, maybe I'll say for each x, because the halting state will be different for each x. There's no one halting state. But if we have a stopping time tau, a single one, so that for each x we have a halting state, then tau is an optimal strong stationary time. So then tau is really the best. And this is quite powerful, but also immediate to prove. Because let's look at this proof of the inequality. Where was the only step of inequality in this argument was right here. Everything else was equality. But if y is a halting state for x, then this step becomes an equality. Right? And then everything else I said here was equality. So if y is a halting state, then if xt is y, it means I'm already at y, so tau must be at most t. So this event is the same as this event in that case. So we have equality, and everything is equality. So this tells you some information that, for the hypercube, well, it's pretty intuitive that this is a good strong stationary time, but in fact, it's optimal. So now, any questions about that? Okay, we're finishing in 1 minute. Let's look at, yes?
If you have a strong stationary time, then probably the extra equal to y has to be always this or it is pi of y.
Probability that of what?
Piece of x tau equal to y.
Probability of x tau equals y is exactly pi of y.
Yeah, but then you'll extract
This is the probability that xt. So this quantity here, this quantity here could be is negative for some choices, right? So this ratio. So this is a what's written here is a t, not a tau.
But if equality holds, the right hand side is not negative.
Yeah, when equality holds, that's right. So at the halting state, so when we say equality holds, the equality is not. Okay, so you have a good point. Yeah, I have to correct this. If so, equality holds for all x. Thank you. No, this is a. Yeah, no, that's a. Thank you. Yeah, that's a good point. Yeah, what was written there was wrong. I did the quantifier too generously. It's Sx of t is just a function of x, not of y, and we maximize over y. So if I take these quantities and I average them with weight pi of y, I'll get 0. So the average is 0, hence the maximum is positive. And that's the right thing. Okay. So when I say inequality, what I want is this equality. So, thank you. So the equality is achieved for all x if I can find a y which gives the equality. It's not for all x, y like I wrote before. Thanks, Krishna. Okay, so that's so the last thing is just about look at the top to random insertion. We define the strong stationary time there, which is when the bottom card reaches the top plus 1. Is that a strong that's a strong stationary time? Is it optimal? So look at the chain which was the top to random insertion on n cards. We defined a strong stationary time there, which is the time when the bottom card reaches the top plus 1. So ask, is that strong stationary time optimal? Well, I already tell you it's not optimal. There is a better one, which is, it turns out you don't have to wait till the bottom card reaches the top. You can wait till the originally second to bottom reaches the top, plus 1, and that's also a strong stationary time, because it still has the same property that the cards under it are in relative uniform random order. So you have these n cards, and you focus on this one, and as cards move under this one, the relative order of the cards under this one is still uniform. And so the same argument applies. If you wait till the second to bottom card reaches the top, plus 1, that's also a strong stationary time. And that one is optimal. So why don't you think about that? And I'll stop here.